Okay, welcome everybody. It's a pleasure to have Laurin Köhler-Schindler talk about the Russo-Summer Welsh theory for positively associated percolation. Thank you very much.
Thank you very much for the introduction and to all of you for the invitation to talk about Russo-Summer Welsh theory today. What I plan to cover is to first introduce Bernoulli bond percolation on the square lattice and talk about Russo-Summer Welsh theory there, who was known. And in particular, I will also emphasize the role of independence in this context. And once we have studied that, I will talk about general Russo-Summer Welsh theory for positively associated percolation in the plane, state the main theorem, and try to give you some ideas of the proof. So let's begin with Bernoulli bond percolation on the square lattice. We consider the graph G with vertex z given by z2 and edges being nearest neighbor edges between the vertices, as shown on this piece of z2 here on the slide. And for some parameter p in the interval 0, 1, we remove edges independently of each other with probability 1 minus p, which means that an edge remains with probability p. So when we have done this, we might end up with a realization like this one, where some edges are removed and not there anymore, and the edges that are remaining are colored in red. The main question in percolation theory is the following, namely what the connectivity properties of this remaining random subgraph with edge set omega are, whether it is connected, how large the clusters are, these kind of questions. And I want to very briefly emphasize this here. So in particular, if we would choose P to be equal to 0, then clearly there are no edges remaining. So omega is just the empty set. There's every vertex is a singleton. Whereas on the other hand, if P would be equal to 1, then all edges are remaining. So omega just equals the original edge set. Now the natural question is what happens in between? And it is well known in percolation theory, in particular here on Z2, that there is a critical value PC such that below this PC, there is no infinite connected component within this red set of edges omega, whereas when we are above PC, then we have a unique infinite connected component. Just to be sure, you can see down to the bottom of my slides.
It's a little bit cut.
No, cannot. The bottom is cut off.
Okay, so let me try to fix that quickly. Is it better now?
Yes.
Okay, great. Thank you. Sorry for that. So the natural question, once we know what happens above and below PC, is the question what happens at PC, so at the critical point. And this is exactly where the Russo-Summer Welsh theory comes in. So I now write P subscript P for the measure associated to Bernoulli bond percolation. And an initial first observation that one can make is that when we consider a square here, we will either have a path crossing from the left side to the right side that is connected in omega, or we will have a blocking path of edges that have been removed in our procedure. And interestingly, if we choose P to be exactly 1/2, then the role of removed edges and remaining edges is the same one. So by symmetry, we obtain that for P equals 1/2, actually the probability of crossing a square from left to right is always equal to 1/2. This is very special at this point p equals 1/2 and allows for a very natural question. If we can cross these squares with some probability, how about other shapes? How about, in particular, long rectangles? And this is exactly the question that Russo-Sommer-Walsh theory answers in the following way. Thanks to a theorem by Russo and independently Seymour and Walsh in 1978, we know that for Bernoulli bond percolation, for any aspect ratio of the rectangle, so for any aspect ratio lambda, the probability of crossing a long rectangle is bounded below by some uniform constant that does not depend on the scale. So this holds for all scales. This is interesting because these long rectangles allow for much more complex and interesting constructions than just having a square available. And in particular, it allowed Keston in 1980 to prove that PC is actually equals to 1/2 and that at the critical point PC, there is no infinite connected component in omega almost surely. Later on, it then became one of the building blocks in the study of critical and near critical planar percolation, and first for Bernoulli percolation, then also for other models. An example for the critical study would be the study of arm exponents or the convergence to SLE6. The near critical regime, it plays an important role when studying scaling relations. What would be the first natural attempt to try to prove such a Russo-Sommer-Walsh statement, namely to prove the existence of a crossing in a long rectangle? One thing that one might try is to just take two paths, a first one in this first square and a second one in this slightly translated square. And now somehow we would want to connect these two paths in order to create a path in the long rectangle. For that, we could just put another square, just like centered right in the middle, have the idea to connect these two paths now with a top-down path in this additional rectangle. So let me draw this one in blue, but in the same way, it's an open path as before. So maybe we'll try to draw a path that is nicely connecting these two red paths here. But what is the problem? The problem is that nothing guarantees us that this path is actually behaving nicely and intersecting these two paths, but we might actually see a behavior that this path surrounds the other paths, so we do not build a connection from left to right in the long rectangle. And this is a behavior that we call meandering of paths, as indicated in this picture here by a river that meanders, that we have no tool a priori here to exclude this very fractal behavior of the paths, which basically always do what we don't want them to do. Having made this initial first attempt, the natural second attempt would be to say, okay, if we're able to cross a square, maybe we can say a bit more. Maybe we know where exactly the crossing occurs. And one thing that one can show, and we're not going into the details here, is that as soon as one has a square crossing, actually one can show that the crossing starts at some small region, let's say n/100, that is centered on the left and reaches a centered region on the right. This would be a second step that one can rather easily obtain. So show that this event actually occurs with a probability that is uniformly bounded from below. This looks already better because we might think, okay, now we are in good shape to do the same argument as before. But as most of you probably already guess, we can actually get the same problem. So this path might again meander through the other paths, and we don't manage to actually create a connection from left to right because this path just meanders through the other ones. what we see here is that the path actually needs to meander even more because we have this constraint where the paths end. So it really needs to go nicely through this corridor region here. So far, I just told you what doesn't work to prove Russell-Samuel's theory for Bernoulli percolation, even if they are very natural first steps. So let me give you a rough idea how we could now use the independence of Bernoulli percolation to actually prove the Russell-Samuel statement. And here the idea would be to explore the lowest path that crosses the rectangle from left to right, so this path here. And importantly, in order to explore this path, it suffices to explore all the edges below the path to find the lowest one, meaning that we don't know yet what happens above, and this behavior of the Bernoulli percolation above the lowest path is still independent of what we have discovered so far. And if in this context we condition on the path, then the idea would be, okay, now we reflect this path. This is just a deterministic reflection of a deterministic path. And now if we make the same argument as before, so we draw our blue path in here, we make the following observation: conditioned on this lowest path, it will either hit the red path on the left, or it will hit the gray path on the right. And these two things by symmetry are equally likely. So that is a way to exclude this meandering behavior of the paths, because we actually need to hit one of them. But this only works thanks to the independence property, because what happens above the path that is discovered is still independent of what has already been discovered. So this is how independence can be used in the special case of Bernoulli percolation. Are there any questions so far? Okay. So let me summarize what we have used in this proof for Bernoulli percolation, even if it was, of course, not a complete proof. We have used symmetry of the measure, namely that our Bernoulli percolation measure is invariant under translations of events, pi/2 rotations, and also horizontal and vertical reflections. This is what plays into the proof when we move around our rectangles or turn them to have a path from top to bottom. A second important thing that we have used is positive association, which is often referred to as the FKG inequality. And to introduce that, I quickly need to tell you what an increasing event is. So we call an event increasing whenever it is, morally speaking, favored by open edges. So let's say we have a subgraph omega that belongs to our event, and then we have another subgraph or set of edges omega prime, which contains more edges. So it's larger than set omega. Then we want that omega prime is also contained in the event. This is exactly saying if it's an event of the type that when we add more edges, we can only remain in the event, we cannot leave the event anymore. And the most important example for this talk is really just these crossing events. So the event that there exists a red path in omega that goes from the left to the right, or in other examples from top to bottom. Having defined an increasing event, we can now say what positive association is. So this measure is positively associated, meaning that for increasing events, the probability of the joint occurrence of two increasing events, E and F, is larger than the product of their probabilities. This intuitively makes sense because let's say you want an open path gamma 1 from somewhere and a path gamma 2 somewhere else. Once you have this path gamma 1, maybe your path gamma 2 will profit from the fact that it can already use edges that are open thanks to, or that exist thanks to gamma 1. So it's easier to have this second path come here. This is what we call positive association, and in the case of Bernoulli percolation has been proven by Harris in 1960, and the name FKG inequality goes back to a much more general proof by Fortuyn, Castellan, and Ginebra in 1971. The third property that we have been using is this independence property, namely that the fact that an edge is contained in omega, let's say an edge E, is independent of the fact that an edge F is contained in omega for different edges E and F. These are the things that went into the proof. After the initial proof by Russo, Seymour, and Walsh, there have been many extensions of this Russo-Walsh theory, since it has proven useful to study critical and near-critical percolation. And I would like to mention a few of them. There's a first line of argument which is somehow similar to this exploration of the lowest path that I have shown you for Bernoulli percolation, namely relying on a domain Markov property, which we have in many different models. And in these type of arguments, we've seen it for Bernoulli percolation. It can also be used to prove Russo-Walsh for Boolean percolation. I should put a 2 here. Which was done by Roy and later by Alexander in a stronger version. And an important example is also FK percolation with cluster weight Q bigger or equal to 1, for those who know, where the Russo-Walsh theory has initially been established by Beffara and Duminier-Copin in 2012, and there has been a lot of work there later on to get more precise and refined Russo-Walsh statements. These arguments relied on an exploration argument, and now there's a second group of arguments which lead Russo-Walsh theories, namely using symmetries, positive association, and a quasi-independence assumption. This was originally introduced by Bolobash and Riordan in 2006 to prove the theory for Voronoi percolation, which has spatial dependencies, so no domain Markov property, and later strengthened by Tassian in 2016. And this has also allowed to study Russo-Walsh results in much more general models, for example, studying nodal lines of Gaussian fields that are positively correlated and have a sufficiently fast decay of correlations, which was initiated by Beffara and Gaia in 2017. Finally, in this case, when we don't take an additional assumption, so we only assume symmetries in FKG, there have been weaker results also by Tassian in 2016, which are basically a Russo-Walsh statement which does not hold at all scales, but only along a subsequence of scales. That being said, the main theorem that I would like to talk about in this talk is the following, namely when we consider a general bond percolation measure which only satisfies symmetries and positive association, so no additional assumptions, then as soon as we have a uniform bound on crossing squares, let's say by some constant C1, then we also have a uniform bound on crossing long rectangles of any aspect ratio. This gives a unifying proof of all the models that I've mentioned before, because as you see, we only rely on these two assumptions. So the proof that we have here and that is joint work with Vincent Tassian, actually works in all the models that I've described before. Actually, for applications, it might be interesting that this theorem can be generalized. So I would like to comment on that quickly. First of all, everything that you've seen so far in my talk has been on Z2, so on the square lattice. This is only for presentational purpose because it's nice to work with the square lattice, but actually all the ideas work for general percolation processes in the plane. So you could take other lattices with sufficient symmetry. You could consider crossing events that are induced, let's say, by positively correlated Gaussian fields, and so on and so forth. You can work with Voronoi percolation. So it's really robust in general. The second thing that I like a lot is this, that we actually, even if we work with a renormalization approach, as in the previous work of Tassion and Bolobosch and Riordan, we actually obtain a one-scale relation between short crossings and long crossings. What I've shown you previously was, I said we assume a uniform bound on squares, and then we get a uniform bound on long crossings. What I state here is that actually it suffices to assume something about the crossing probability of a short rectangle at one scale to deduce a bound in terms of for the long crossing at the same scale. And here I've written that there exists a universal homomorphism that you can just think about a picture like this. So the graph looks something like that. So let's say the short crossing occurs with probability 1/2, then maybe the long crossing only occurs with probability 1/1,000,000. But it's strictly positive, and interestingly, the probability goes to 1 as the probability of the short crossing goes to 1. Finally, the ideas can also be extended to finite volume, for example, to FK percolation models with boundary conditions at finite distance. For those who know about FK percolation, so for example, if we consider free boundary conditions that are just at some macroscopic distance from our crossing, then we can show that the probability of crossing a long rectangle is again bounded by a function of the probability of crossing a short rectangle. Are there any questions on this statement and the extensions?
Do you have matching lower bounds for psi?
You mean matching low? You mean whether we have? Can you specify? You mean whether these bounds are good?
Find some model which satisfies symmetry in FKG where the psi, the universal psi, is in fact the exact one?
No. So it's a very good question. Thank you. This psi is, in that sense, not quantitative at all. So the psi that we get is probably a function like it's a power of 10 billion involved with another square root trick. So it's really not at all optimal. We have tried to optimize a bit, but I think the strategy we have here will never give an optimal psi in this context. Unfortunately not. That would be very nice, but it doesn't work here. Any other question? All right. So let me try to explain the main idea of the proof of this theorem here. So we assume a uniform bound on crossing squares, and now we want to prove a uniform bound on crossing long rectangles. So jump to the proof. So let me recall these meandering paths that I've talked about before in the context of Bernoulli percolation. There we basically saw if our proof doesn't work, so it does not directly give us a Russo-Sam-Walsh statement, that was because the path was meandering, so it was sneaking through this corridor here. Actually, when we now zoom in and ask ourselves, what is the path doing here? Then we can again check that the path has to meander even more, because otherwise we would obtain a Russo-Sam-Walsh statement there. More precisely, if I draw it here, so we see this middle part of the left rectangle here on the right. Then of course I might again force some crossings of squares, which I know how to create. Let's say here. And if I consider this blue path that I've drawn here on the left, then actually I can see that it needs to meander again and go through another corridor here. And this story continues and continues and continues. So the further I zoom in, the more meandering I will always see of my path, because if at no point it gives me a Russo-Sam-Walsh statement. So whenever we have no Russo-Sam-Walsh, then our paths are meandering, and we can think about them as a fractal curve, or actually when we really go deep into the scales, as a piano curve that basically covers everything and winds a lot.
This is only, I mean, this is only in the limit, right? I mean, the larger n gets, the more it can meander, but obviously for fixed n, it cannot meander arbitrarily. I mean, these things are discrete.
Indeed, that's a very good point. Thank you. It cannot meander arbitrarily. In that sense, it's just a picture that we're using here for a discrete fixed n. The idea is we want to show something when n becomes very large, and what we will actually show is that it meanders for a while up to some scale where we refine Russo-Sam-Walsh. So if you take up the discrete example, as you said it here, because indeed we are on a discrete lattice, then when you go down to just one vertex, of course you have a long crossing, because the probability of just having, let's say, one vertex or just two vertices in a row, let me draw it here. If we just consider a very small rectangle like this one, then clearly with a positive probability, I will see that these three edges are open, which actually occurs with probability at least p to the 3. So in that sense, when we really go down to the point where we see the discrete lattice, then we are on the safe side, because there we know how to construct long crossings. Does that answer your question?
Sure.
Okay, cool, perfect. So we will see exactly this point now in a second, but the mental picture I would like to give you are exactly these meandering paths that go down through the scales. So let me introduce the main object that will formalize and allow us to quantify this meandering behavior, which I will call quasi-crossings. So here I will assume for the moment that for some scales n and a lower scale m, we have no Russo-Sam-Walsh initially, meaning that for some well-chosen constant c prime, actually the long crossing of a rectangle at scales L between m and n does not occur with probability more than c prime. Actually, it occurs with probably strictly less than c prime. Having the meandering picture in mind, this means when I consider a square crossing in this square here of size n by n, then this path meanders a lot. And in particular, if I don't have Russo-Sam-Walsh up to scale n, it must connect to some short crossing of this box here. So drawing that more nicely, the meandering idea allows me to show that actually there must be a crossing of this short rectangle at scale m that is part of my square crossing, because my path is meandering a lot. When I symmetrize this picture, so I take a second square crossing as before. So here you see the path in red from the left, and I draw a similar thing from right in blue. So where I consider the blue square crossing, which will also have to connect down to this scale. And this is what I would call the quasi-crossing. And let me describe it, just be on the safe side. So here we see crossings of this rectangle at scale m, short crossings, which are connected to the left and to the right. This is a quasi-crossing. And the key step in the proof is to show that under this assumption of no Russell-Sum Walsh between scale n and m, the quasi-crossing from n down to scale m has a probability that is strictly bounded from below, say by C prime prime, which is a different constant that does not depend on n and m. So let me summarize this main step. If we don't have Russell-Sum Walsh, then our paths meander. Therefore, square crossings at scale n need to connect down to scale m, and that's why we obtain these quasi-crossings with good probability. Let me now convince you that these quasi-crossings are really nice because they allow us to conclude the proof once we have done this key step, which I will jump for the moment. So we want to prove the theorem, meaning that our goal is to show a uniform lower bound on long crossings. So let's fix some n where we now want to prove that the probability is bigger than C lambda. Now we choose the largest scale below n where we have a Russell-Sum Walsh bound, namely the probability of crossing a long rectangle is bounded below by some C prime. In the picture, we see it here. We start at some scale n where we want to prove Russell-Sum Walsh. Then we check where we have the first time a Russell-Sum Walsh with this constant C prime, and we call this scale m. So we see that below the two scales, there is no Russell-Sum Walsh with C prime, and at this scale, we have Russell-Sum Walsh with the constant C prime. Thanks to this key step that I tried to motivate before, we obtain that the quasi-crossing is bounded below by another constant C prime prime, the quasi-crossing from n to m. Now let me try to conclude the proof of the theorem. So let's say we want to bound this probability of a long crossing at scale n from below. One way, I will zoom a bit so you see it more clearly, would be we force a quasi-crossing to occur, namely to have a path that comes from the left and connects to this little rectangle here at scale m, as well as a path from there that goes to the right. This is our quasi-crossing. And now we glue in a long crossing at scale m to connect these two components and form a long crossing in the large rectangle n. So we, in some sense, I zoom out again, we teleport this Russell-Sum Walsh that we have found at the lower scale m and bring it back up to the scale n. And how does it work? As I described, we construct this quasi-crossing that we close with a crossing at the lower scale. Now we use the positive association to see that this is just larger or equal to the probability of a quasi-crossing times the probability of a Russell-Sum Walsh long crossing at the lower scale. By the key step, this is at least C prime prime. By assumption, we have Russell-Sum Walsh at this low scale. So combining these two, we get that this is more than C prime prime times C prime, which we might call C lambda, concluding the proof. So this quasi-crossing is really the quantity that allows us to transport Russell-Sum Walsh from a lower scale up to the higher scale without losing in probability. Of course, I started here with a Russell-Sum Walsh at C prime, and now I get something at C lambda, but this bound is not degenerating. I have this slightly stronger Russell-Sum Walsh, which is the C prime Russell-Sum Walsh, and the slightly weaker Russell-Sum Walsh with the C tilde, the C lambda Russell-Sum Walsh. But all I wanted to do is to prove a uniform lower bound, so this is sufficient. Are there questions at this point?
I probably missed something, but
Yeah.
it seems to me that you've shown something that depends on a particular n. The larger n gets, the smaller this could get. Why is it uniform?
Yeah. So I wanted to claim that this is uniform. This is basically the key claim, but indeed I didn't tell you why it is uniform. The idea behind it is that we have this meandering path, and as long as we don't find Rousseau-Walsh, it needs to meander lower. But indeed, the big question is, why is that uniform? So maybe let me try to invest a few more minutes to convince you why this is a uniform behavior. So this would be exactly. So the argument why we are able to obtain this uniform bound on the quasi-crossings is thanks to something that we call a cascading property. So there are two steps involved in proving this. The first step, and I suppose that this is the one that you will quicker believe me, is the fact that when we choose scales that are close to each other, so in this case n and n over 2, then I can construct these quasi-crossings. It's basically, I saw that my path meanders, and it in particular, it meanders to scale n over 2. And since this scale is within finite reach, I get a uniform constant here. This, of course, doesn't tell me anything yet about meandering down to lower paths, and that is where the cascading property plays in, which is precisely what I wrote here. So when we consider any three scales, L, M, and N, then we can bound the sum of the probability of the quasi-crossing from the highest scale to the lowest scale, from N to L, plus something that is looking like a long crossing is at least the probability of crossing of the quasi-crossing from M into M. So let me put that here. Exactly. And let me try to convince you of this. So once we have this statement here, the idea would be to prove our uniform bound inductively. So starting with something that is within finite reach, using the fact that the second term here is small because we have no Rousseau-Walsh. So the first term needs to be large in terms of this one. So in particular, it needs to be bigger than at least half of that probability, and then we can inductively take this probability up. Maybe that was a bit too quick, so let me try to at least convince you of this inequality here, which is really at the core of the proof. Let's consider the event that we see on the right here. So the quasi-crossing that comes from scale n and meanders down to scale m. So out here we have the big scale m, here we have the intermediate scale m, and the small scale L. What I've drawn here is a quasi-crossing from the large scale n to the small scale n, to the intermediate scale m. So at this point, theoretically, you could just forget about this inner one. Now we can differentiate basically two cases. When we consider the behavior of these meandering, of these parts of the event. So either they will actually, let me remove them for a second. Actually, when we consider this third scale, which is lower, they will either go through this, will actually connect down here. I've drawn that a bit badly, so let's say this is that. So either on the event Q and M, we also observe the event Q and L, or if this is not the case, let's say I take this red path, then this red path needs to actually do something non-typical and maybe behave like this. But as soon as I have a path which does not meander sufficiently to go down to the scale L, I can do the following thing. So let me erase this. Let me just keep this path which I've just observed. So I remove everything else. So just have this one single path that we see here. If I now intersect this path, this we call maybe a good path. If we now intersect it with the event Q and L, then what do we observe? So sorry, the event QML. Now I draw them in here, and since this path was not crossing the small rectangle, it must somewhere intersect this new structure. And thereby now obtain a path which is actually, we have an intersection somewhere, so this path is somehow connected to the left or to the right, which can be shown to be a strong Russell-Sum-Walsh statement, so then we are done. So to wrap this up and formulate it maybe easier once more in a short way, either our path will always manage to meander to lower scales, or it will have a behavior that is not meandering at some point and therefore gives us Russell-Sum-Walsh there. And from this point, it's just an analysis to use this inequality to actually see that there's a uniform bound coming up, because the right-hand side here, when we choose N and M close together and we go inductively up, will not degenerate. Did that roughly give an idea how we proceed, how we keep this bound? So then I think, even if it's just 1:45, I would stop here and allow you a bit more time for questions on these paths.
So thank the speaker. Any questions?
I had a question.
Yeah.
Sorry. I wanted to ask whether you think the symmetry is required. That is, something probably is required, but to what extent can it be weakened? Recently, I was thinking about percolation and circle packings, for instance. Maybe already that's enough if you're in a nice regular structure like a circle packing, but they don't have to be symmetric in any way.
Mm-hmm. It's a very nice question that I actually also like to think about, the question how much we use these symmetries. This strategy of the proof requires at least some symmetry, so we cannot erase them all. And maybe it's a good point to give you a counterexample why we need at least some symmetry.
Yes.
So let's say we consider the following one. We just consider a deterministic picture, so a very simple drawing. Let me say we are on the square lattice, and now we consider just like these diagonal ladders that are going up here. It's not a beautiful drawing, so I will just draw them as diagonals now. This should just be viewed as a deterministic picture with these diagonals going from bottom left to bottom right. What I can check is that when I look, let's say, at a square here, I will always find a diagonal which is just crossing this square. And in particular, when I consider an easy crossing, so a short rectangle, let's say this one, then it will always be crossed. So the probability of crossing a short rectangle will be 1. Whereas when I consider a long rectangle here, it will never be crossed from left to right. So in that sense, I need at least some symmetry, and just assuming that all short crossings are crossed is not sufficient. In some sense, the building blocks that I need everywhere are some events of this type. So if you can show that is a crossing, an easy crossing of a rectangle like this and like this, occurs everywhere in your plane, then the proof strategy tells you that from there you can just put them together to create quasi-crossings. You don't need any more symmetries. But you initially need some symmetries to show that these events here actually occur in our, at least in the way we prove it. I think Bolobash and Riordan have some work from 2010 on actually, I think, Bernoulli percolation on self-dual polygons, where they really work with no classical symmetries, but this proof requires at least some symmetry.
Okay, thank you very much. Very nice.
Maybe I can use this chance before I get the next question to give you a counter example also for the case when we don't have positive association, which might be a natural second question. So if we again just have these diagonals, but this time we don't view it as a deterministic picture anymore, but we toss a coin whether our model looks like this or it looks like this, with probably 1/2, 1/2. This has all the symmetries that we want. It clearly does not have positive association, and in the same way as before, long rectangles are not crossed. Are there more questions?
Not so. Thank you very much again. And the next talk starts in 10 minutes.